what is the inclining experiment for? Corey H., do you remember what we used the inclining experiment for?
Those were the weights, right?
Yeah, well, it turns out that you get the boat from the shipyard, okay? But at this point, okay, the boat was built, it's got a certain shape of a hull, okay? Well, what we want to do is we want to determine, we don't know where the kg of the vessel is, okay? We have an idea, but we don't know where it actually is, okay? We want to be able to measure this very precisely, okay? We want to be able to measure this kg very precisely of the lightship. How hard is it going to be for us to know what the displacement is of the lightship? Is that going to be hard? Why do you say no? Yeah, we can just read the freaking draft marks. The shape of the hull is going to determine the draft. I mean, the shape of the hull is going to determine what the displacement is at any draft mark, okay? And since the architect knows the shape of the hull, the displacement is going to be known. But, you know, let's say, well, the engine weighed about this and da. We don't know exactly. They have a pretty good idea of where the kg should be, but don't know exactly where it is. And remember that every calculation we're going to do in the future is going to be revolving around this initial weight. What's the biggest weight that any vessel will ever carry? Itself. Now, I don't know if that's 100% true for like, you know, you could have a heavy lift, okay? I don't know. I mean, I could like, I'm 225. I think I could probably, you know, carry somebody maybe 300 or something like that. I don't have the strongest legs. I don't think you know, I think they'd be going like this. Okay, so, you know, maybe I could do 300, okay? Okay, well, maybe there's some heavy lift ships that can lift more than themselves. I don't know. I've never really thought about it. But pretty much any other vessel, every weight that they have is going to be, any individual weight is going to be less than the actual weight of the ship. Okay? Any individual weight is going to be less than the weight of the ship. We need to know this kg. Because if we don't, all of our TOM calculations are going to be pooched. Okay? So, this inclining experiment is literally how it is done. This is how it's done. Okay? It's an experiment where you go out and you do a little something and you observe data, you collect it, and you replicate it. You do it several times to try to get, you know, a consistent pattern. Okay? The only thing that is so this is really a scientific method. Okay? The only difference is that you don't have to shop it out to another lab and have them do the same thing and compare your results. It's just going to be done by one group coming in. Okay? You're not going to have like a second group come in and do it and a third group come in and do it. You're going to do multiple experiments in one run. You're going to move weights around back and forth a couple times. I'll show you that. So we place a known, and we talked about all this already. Okay, you place a known weight, a known distance off the center line. Okay, and when we move that weight, okay, so here's a weight. Oh my God, you gotta be kidding me, it's a brand new marker. So we got a weight, okay? That one sucks too, okay? And the vessel's upright, no incline whatsoever. Well, what's gonna happen if I move this weight? So this is a weight, and this is a distance, okay? Oh, weight times a distance, that's a moment, isn't it? Yeah. And I want to know the whole kg. So, all right, well, you know, weight times distance is, this is the formula we're going to be using. GM is weight times distance over displacement tan theta. Hey, does that look like anything familiar? Weight times distance divided by displacement? That looks like shift to G to me, doesn't it? When I throw in the tan theta, it's not GG anymore, it's GM, okay? But GG is actually in there, okay? So anyway, this is kind of interesting. So let's say I had a weight that was like, I don't know, I had a weight of like 2 tons, and I shifted it, I don't know, like I shifted it like 20 feet. Where do you think the 2 tons would go in this formula? Oh, so this weight is the weight that you're shifting, okay? So the W is the weight you are shifting. Okay, so that's, in this case, that's going to be 2 tons. What do you think the D is? Okay, it's going to be the distance you shift. Cool. All right. So, Chris, I'm trying to calculate kg, the freaking center of gravity of the whole damn boat. What displacement am I going to use in this problem, in this formula? Yeah, the entire displacement of the boat, including the freaking weight. Okay? Displacement equals displacement of ship, including the weight that you're freaking around with. Because it's on the ship. Now, this is not normally part of the ship, but we need, it could be, okay, but normally the Coast Guard brings a weight, or you provide a weight, okay? You're gonna have to deal with that at the end. Anyway, so this is 20. So if it's 2 tons and I shift it 20 feet, and my displacement is, let's just say that with the weight on there, let's just say the displacement is, I don't know, 1,000, okay? What do you think this tan theta is going to be? What's going to happen when I shift that weight over there? Oh, I'm going to create a list. I'm going to get some kind of angle. So let's say when we do that, we get an angle of, let's say, I don't know, 2 degrees. It creates a 2-degree list. Well, that's going to go here. Okay? All right? And we're certainly going to use this formula for some stuff. But when we're doing the inclining experiment, how do you think I'm going to get this 2 degrees? How would you get this 2 degrees? We're going to do this, and then we're going to see, we're going to observe 2 degrees. So, okay, we're going to take a known weight, we're going to move it a known distance, we're going to know the displacement, and we're going to get an angle. How am I going to know exactly what that angle is? Yeah. Okay, yeah, okay, so I could use like the inclinometer that you got up on the bridge, but that's not precise enough. So I am going to use a pendulum. Okay, I'm going to use a pendulum. I'm going to make this pendulum hang down, okay? I'm going to make it as long as it possibly can be, okay? And then what I'm going to do is down at the bottom, I'm going to have a bucket of water, okay? And I'm going to let the weight that's on the end of that thing sit in that bucket of water, okay? Cool. Now what I'm going to do is I'm going to strap a batten, a piece of freaking wood, literally a batten, okay? I don't know if there's 2 T's in that. I think there's 2 T's in that. Anyway, okay, batten. I'm going to strap a batten to the top of that thing, okay? And what I'm going to do is I'm going to mark, when the vessel's upright, I'm going to mark exactly where that wire meets the batten. What's going to happen when I move that weight? What's going to happen? Okay, so the vessel's going to incline a little bit, right? Because I moved the weight. And so this is still the center line. Look, the batten is running down the center line. I mean, not the batten. The plumb bob right now is running down the center line. But what's going to happen when I incline the vessel? The freaking thing is still going to be vertical. And now I've got the bucket of water here, and I got my batten. I'm going to mark there. And you can see that the pendulum deflected. You see the pendulum deflects a little bit. What kind of angle does that look like to you? Right? If that's a right friggin' angle. Do you think on this batten that we can measure that distance? It would probably be in inches, right? We're freaking Americans, we use inches, right? We don't use that metric crap. Metric's beautiful, okay? But anyway, use a lot of that in the engineering, okay? We don't use a lot of that in deck, but it's beautiful stuff. Huh. I know that distance, I can measure it. Do I know any other distances? Oh. So this is the deflection, and this is the length of the pendulum. And this is the angle. Oh shit, this sounds like freaking trig to me. Opposite over adjacent, which operation is that? Tan theta equals opposite over adjacent. Huh. What is the opposite side? It's the deflection. And what is the adjacent side? Length of the pendulum. So, instead of doing tan 2 degrees, we're actually going to do the, what we're actually going to do is we're going to do weight times distance over displacement, and then it's deflection divided by pendulum. And that is going to give us GM. I shit you not. Okay? That was a derivation. Do you have to memorize that derivation? No, we're math users. We're math operators. We're not mathematicians. I'm not going to make you derive that, but there's going to be multiple forms of this formula, and you might want, and you're not going to have these formulas on a Coast Guard exam. So you're either going to have to be able to derive them or memorize 5 different versions of the same formula. Okay? Anyway, so we're going to take that GM and we're actually going to calculate kg. We're going to do that at the end. Okay? So anyway, we did all that. And you know, this is what it was up on the board. Hey, we're trying to find the G. We're going to do this freaking experiment. And then I started showing you these pictures, right? Did I show you these pictures? Yeah, so the state of Maine, because of, we're looking down at the O1 hatch, because the hatch is in the middle, they didn't put the weights in the middle. So what they did was they put half the weights on one side and half the weights on the other. And then by moving half the weights over to the other side, they had enough weight that the vessel had a noticeable, measurable change, okay? And what do? So they moved half the weights over, so now there's 6 weights. Those are freaking like solid concrete. It's a little bit of weight. Nothing compared to the state of Maine, but enough to make a little bit of a list. Okay. Now, this is one of the escape chutes. Okay. And so, you know, that's down the bottom. We can see the water reflected up from the chamber. This is looking down the chute. This is down in the lower space. Okay. And that's the ladder. So here's the ladder going down. Now we're looking at the ladder, and there's the frickin' tub of water. And you can't see it, but there's a wire that's coming right down, and there's a little thingy in there. Oh, wait. You see this right here, this sort of beige looking line right there? It's actually clamped down with a couple of quick clamps. What do you freaking think that beige thing is? It's the back. So literally, the vessel is upright and the wire comes down, and you take your pencil and you just mark, get a straight edge, you mark on the back where the upright position is of the pendulum. And then, so that's what you're looking at right there. Okay? So here's the bucket, and then here, this isn't the one for the state of Maine. I got this off, I don't know. I got this from Set Sail. Okay? But that is actually a nice piece of wood right there, and you mark it with the pencil. Then we move the weight. On the state of Maine, the weights are outboard, shifted over. Here, we're just going to do it from the middle. Okay? When that happens, batten, rotates with the hull, but the pendulum stays pointing to the center of the earth. That's 90 degrees over there. There's theta. That's the deflection. And you literally, once the vessel settles out, you take your pencil and you mark the batten. Oh, that was the original spot. This is the new spot. You measure that. You also have measured this distance quite carefully as well. Measured. Deflection pendulum. How long do you think that deflection is going to be? I mean, literally, it's probably going to be maybe that much at the most. How are we going to measure that? What units are we going to use for that? Inches. What do you think we're going to use for the pendulum? Feet. Because that might be, on the state of Maine, that might be 30 feet. So we're going to have a problem here. In all the problems I'm going to give you, the deflection is going to be in inches and the pendulum is going to be in feet. So you're going to have to convert inches to feet or feet to inches. But anyway, we'll get around to that. Okay. Okay. Cool. These are actually battens. These are battens. They did this. They set up 3 pendulums on the state of Maine on 3 hatches, 3 escape chutes, and they measured it on all 3 of them. So they was doing replication in one shot. Okay. And you can see those pencil marks right there. Okay. The pencil marks. Oh, look at I moved my chair. My chair was there to keep me from going over there, getting out of the camera. Okay. Anyway, you can see those pencil marks. So that might have been when the vessel was upright, and then this was, you know, they moved the weights to port, they moved the weights to starboard, replication. You know, without going into any great detail, you know, you want to make this as exact as possible. So you get rid of any extraneous weights. So if you have like a whole bunch of yard workers on there, you send them off. Okay. You'd like to get your lines all loose. You got your lines going through the bulwarks. They have catenary. They're going to influence the vessel. So typically what you do is you put the lines down very low. And you also see that line is very slack. You don't do this on a windy day. Today would not be the day to do the inclining experiment. Because when the boat comes hard up on its lines, it's going to affect the angle. And if the angle is off, calculation is off. That means the rest of your freaking calculations from there on in are off. Okay? So you try to have, like, it'd be best if you had no fuel, no water, just the light ship, all the equipment installed. And here they took the freaking bow lines and they kind of went, instead of like having them up, they went around and blah, 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 whatever. Okay. So anyway, I already drew this on the board, but that's what's going on. Okay. So there's the deflection. I must be going through puberty. My voice is breaking today. Woo. Second, it was like a hobbit, you know, second breakfast, second puberty, I don't know, something like that. Okay. Anyway, maybe, yeah. So anyway, so the angle, we already did all that. It's already done. Okay, you can go back and look at that, whatever. Now, there's a page in your book. Now, this is kind of the cool part. I'm not going to linger on it too much more, though. On your page, in your book, on page 113, you'll see this picture. What they're trying to do is get that freaking mask up above your nose. Yeah. Okay, thank you. So, what they're trying to do is show you, this is the inclining experiment going on over here. This is how we calculate our kg. But over here, they're showing us something else. They're showing us that, hey, you know what? There's another triangle that's being made, and it's a triangle that involves, well, GG and GM. And they're actually the same triangle, which means they're related, which means we can start to move bits and pieces from one into the other. And when we do that, we're going to end up with this formula. Okay? So, on the left is the inclining experiment, and on the right is angle of list. It's really the same formula, but some of the problems I'm going to give you are calculate the kg of the vessel by the inclining experiment. That's going to be this form, where I give you a batten deflection and a pendulum. That's one form. If I ask you to calculate the kg of the vessel using the inclining experiment, if your deflection is 3 inches and your pendulum is 30 feet, you're going to use this form of the formula. And you're going to eventually be able to take this and calculate kg. However, I might say to you, you know what? You already know what your kg is. But now you're going to lift something. You're going to lift some X number of tons, and it's gonna be overboard the side. What's your GM gonna be? I want you to calculate what that's gonna do to the ship's GM before you do the lift. Well, we're not gonna use that version. We're gonna use this version, because we're gonna be looking at an actual angle. Okay, so this is two sides of the same coin. If you're asked to do a problem where you are calculating the kg of the vessel, you're going to use this one, the inclining experiment. Okay, the inclining experiment. But we can use this formula to calculate all kinds of other cool stuff, not of the inclining experiment, that is around the list created by 08. If the problem says, what is the angle of list, or what is the weight to create the angle of list, or what is the distance you would move the weight to create this angle, that's this version of the formula. Okay? So, we move the weights. Both the boats moved over. Okay, I'm not going to linger too much on this, but tan theta is opposite over adjacent. Okay, I'm going to blast through this derivation. You don't need to know the derivation. You just need to know what the formula is. I'm just going to blast through it very quickly, though. Okay, so tan theta in this puppy is deflection along the batten divided by the length of the pendulum. Now, tan theta in this one is actually, see, G went from the center line. If I move this weight over, G is going to move off the center line, isn't it? It's going to shift. And it's going to shift. It's going to shift parallel to this. Okay? Whatever this thing shifted along the deck, it's going to be shifting parallel to that. That's a shift to G. Okay? Huh. Well, that is kind of related to this deflection, isn't it? And then what's over here? That's the opposite. What's the adjacent? GM. So that's what's going on down there is GG. Okay, tan theta in this formula is going to be GG over GM. Well, that's interesting. GG. Last time I checked GG, okay, here's shift of G. That's weight times distance divided by displacement. What can I do now? I can take this and substitute it in for GG. And when I do that, I get this formula. Tan theta equals weight times distance over displacement GM. Does that look like anything familiar? Does that look similar to this formula? What's the difference between this formula at the bottom of the page and this formula? Yeah, this one is solved for GM. The one right there is solved for tan theta. Well, hell, could I solve it for anything else? I could solve it for weight, couldn't I? I could solve it for distance. I could solve it for displacement. Okay. There's two main versions of this formula. We're going to chug one of these things in just a minute. There's the green version, which has tan theta in it. Then there's the red version, where tan theta is replaced by deflection over pendulum. Okay? So, James, if I ask you to calculate the kg of the vessel using the inclining experiment, are you going to use the green one or the red one? The red one. Why? Yeah, that's what I just said earlier, but that's the one where you're going to be using the freaking batten and the pendulum. That's the only way you can calculate the kg. But there's going to be a whole series of other questions where we already know what the kg is. We don't care. We want to know what would be the weight to create, what weight would I have to move 10 feet to create 3 degrees of angle with the displacement of that and the GM of that. So we can solve this. Here's how this works. Okay, I'm just going to put it up there. This top one, the green one, It has 1, 2, 3, 4 different versions of it. It's all just solved for a different variable. Okay? All right? All just solved for a different variable. But when you're doing the inclining experiment, it's only this one. Okay? When we do the inclining experiment, we're always looking for GM. Okay? But this version up here that has the tan theta, not the deflection pendulum, this is the one that we have to screw around with, and we're going to do that on Friday. Okay? So now we're going to do a problem. Okay. So, let's draw a little picture. Okay? Draw a little picture. So, we have a vessel. All right? And its displacement, okay, 3,700 tons. Okay? Now, 20 tons is shifted outboard. 20 ton weight shifted 25 feet outboard from the center line. Okay, so I have a weight. It is 20 tons. How far am I going to shift it off the center line? Yeah, it says 25 feet. So I'm going to move it over to here. Okay, and this is going to be D, 25 feet. Okay? Okay. What else is there? Oh, this, the weight is 39 feet above the keel. Okay. That's interesting. Huh. How long is the pendulum? Pendulum is 30 feet. Right? Okay. So, this is step one. What are we going to do? We're going to move the weight. What's that going to do to us? Now we're going to have this. That's 20 tons. It was moved 25 feet. Its height is 39 feet. Okay? All right? And now we have our batten here. We have our thingy here. Here's our right angle. Okay? So, how long was the wire? 30 feet. How long was the deflection? 13 what? 13 inches. That's what we got. Okay. Huh. This is what we're going to have to do. Calculate GM. Step one. Okay? We're going to do 3 steps. Okay? So let's just do this step first, then there's going to be 2 more steps. All right. Hannah. What am I trying to do here? Yeah, ultimately, I want to calculate my kg. I'm going to start by calculating my GM. What am I actually doing? I'm doing the inclining experiment. So I'm going to use, okay, so the version of the formula I'm going to use is GM equals weight times distance over displacement, and then it's the deflection over the pendulum. Thank you. Okay, let's do it. What's the weight? It's 20 tons. Okay. What's the distance? Okay, now this distance is always the horizontal distance. There's 2 distances in this problem. There's 25 feet, there's 39. We're going to need the 39, but not right now. This distance is always the horizontal, okay, in this application. So that is 25 feet. Okay, cool. Perfect. What is my displacement? Yeah, and that 3,700 includes the 20 freaking tons, doesn't it? So that's 3,700. Cool. Okay, Christopher. What am I going to stick in for the deflection and the pendulum? Yeah, you're Chris.
Christian.
Well, Christian. Oh, that's why. Okay, shit. Sorry about that.
13 inches.
Yeah, 13 inches. Okay, so where's that going to go?
Top.
13 inches. What goes on the bottom?
30 feet.
Do you see a problem, Christian? No. So what are we going to do? We're going to we're going to essentially divide all of it by 12 anyway, okay? You're going to take 13 divided by 12, divided by 30. Anyway, you got to do this, okay? And voila. What number do you get when you do that? 20 times 25 divided by 37 times 13 divided by 30 divided by 12. Okay, that's order of operation right there, okay? I'll simplify this for you. 20 times 25 over 3,700 times 0.036. Okay, that equals 0.036. If you don't get 0.3036, you need to look at your order of operation. What do we get? What is GM? $3.75, you bastards. Okay, 3.75 feet. That's GM. So, okay, just a second. So this is essentially what we have, GM, and that is 3.75 feet. Okay, what's your question?
For the one where it was going from like feet and inches apart, as long as they match, like I did 13 inches over 360 inches.
That's fine.
Instead of going
Yeah.
feet.
Yeah, you converted that to inches.
Yeah.
That's fine.
As long as they match.
As long as they're the same unit. You absolutely can do that. Wunderbar. You came up with 3.75?
0.74.
Oh. Okay, great. So what we just calculated was GM. So here is GM. Okay. Really, it's actually here. Okay. But anyway, the angle is so small, it doesn't matter. Well, what the hell's my kg? How do you know that? Oh, they gave me the km. Now, would your boat give you the km? Yeah. You look at your freaking draft marks, you look it up, it'll be 27.87. So what we've got now is km is 27.87. GM is 3.75. Well, what's kg? Okay, so this is step 2. kg equals km plus or minus GM minus GM. So that's going to be, what is it? 27.87 minus 3.75. What's that? 24.12. That's the kg. Cool? That's the kg. kg of what? Okay. Is that the kg of the light ship? Well, that 20 tons is sitting there. Now, not to mention that you probably didn't have empty fuel tanks, but we're going to have to remove that frickin' weight and its effect. And if you have fuel on board, you're going to have to remove that. And if you got potable water on board, you're going to have to remove that. So when you do this thing, you want to have the least weights on as possible. Okay? Well, wait a minute. That's the kg of the light ship with the weight on it. I need the kg of the vessel itself. How am I going to freaking do that? There are your moments. What is the weight of the vessel right now? 3,700 tons. What is the kg of the vessel right now? Christian? 24.12. So when I multiply those two together, I get bada bang, 89244. Cool. Nathaniel? What am I going to do with that 20 tons? I'm going to discharge it. You're exactly right. So where am I going to do that? Okay, so what kind of symbol am I going to put here? Okay, now, what is the height of that 20 tons? 39. So that is 780 foot tons. What's the sign of that going to be? Negative. What is my total displacement now? Oh, shit. By discharging that weight, I went down to 3680. That's actually the light ship. And my total moments are 88464. Okay? So Sue, these are my total weights without the freaking 20 tons. These are my total moments without the 20 tons. What's my kg? How am I going to do that? Sue? I'm going to divide that by that. Okay? And you should get 24.04. That is the kg of the light ship. If I had fuel on board, I'd have to remove that too. If I had potable water on board, I'd have to remove that too. If I had crew effects on, I'd have to remove that too. Okay? Best to do it without all that crap on it. Okay? It's best to do it when the vessel is like, oh, hey, yeah, we just got it out of the ways, we put the radar on, everything's on, the crane's on, everything's on. Now let's do it before we put fuel and water on it. Okay? Cool. All right.
So technically, if you've got like 4 people on board doing this, you have to subtract them too.
Yes. So, but if you're on a vessel of 10,000 tons, minuscule. If you're on a vessel that's 100 tons, that could, they're all over here. You get on a boat and you put 4 people over there, that's going to be measurable on your deflection. Okay. So, anyway, you want to be as precise as you possibly can, and the smaller the vessel, the more each little thing makes a difference. Okay. All right. Was there another way I could have done that? This last bit? Oh, I could have done shift to G. So if I had done shift to G, how would I have done that? Okay, so shift of G is weight times distance over displacement. So the weight was 20. What was the distance? Okay, 39. What is the displacement? 3,700 minus 20. Okay. When you do that, you should get. Actually, no. It's
25. Shifting the weight.
well, no, it's 39 minus 24.12. Okay, because remember, when you do the shift to G, it's always the G. The G is the reference. Okay? So, if you do shift to G, it'd be 39 minus 24.12. And then when you did that, you would end up with 0.08 down. .12 minus 0.08 or whatever, and that gives you the same 24.04. Okay? So that's it. You're going to have to do problems like that. Okay? This problem was using the inclining version. On Friday, we have 12 problems. So bring your in-class worksheet. It looks like this. Bring this, okay? It's inclining problems, and it's double-sided, and it's actually PowerPoint slides okay? 6 on one side, 6 on the other. We're gonna do those over the next couple of classes. So you gotta bring that, okay? And we're gonna do a couple of inclining problems, but a bunch of the other versions where we solve for weight, we solve for GM, we solve for angle, we solve for distance, okay? And that concludes that. And in the remaining time, I'm just gonna hand out anybody who wants their exam back for a few minutes, and I can flash up the key or whatever, okay? All right, so Jackie, that concludes it. Jax, excuse me, Jax.